Vellum. I'm so excited to talk about Vellum. Vellum is a type of pop simulation, right? It's a branch of it that allows for explicit constraints. This is the big difference between pop simulations and the Vellum world that we're going to explore. The allowance of constraints and some other stuff under the hood makes it a PBD solver, a point-based dynamics solver. And what this means in simple terms is that we have a bunch of points in our scene and constraints that are controlling where those points are allowed to go. Vellum, in my opinion, is the simplest thing to understand, but it's also the most robust. You see, it's a unified solver. This PDB approach to simulation allows us to simulate a bunch of different phenomena from the real world. Things like cloth, soft body, right? Jiggly things, hair, grains, fluid, a ton of stuff. And all of it can interact with each other, except for hair and fluid, by the way. That's just a little caveat to write down. Now, maybe everything that I've said to this point is pure gobbledygook, and you're looking at me saying, I don't like you anymore, and I respect that. So let's break things down even more simply and explore with some absolutely high-end artistic interpretation. You're in for luck because I lost my stylus pen, so I'm just going to use my mouse. In a given simulation, we will have a collection of points and constraints created between those points that limit its motion overall between time steps, right? In a simple example, let's just make a little grid here, a 3x3 collection of points. Oh yeah, I have a gift. Okay, this is a grid, and in between all the points, we will create polyline constraints. Right? Imagine I created it between all of them. I don't really need to for this one. But these constraints are given limitations, or really a collection of different attributes that we can curate in order to control the motion that these points are allowed to have. And the two that I want to introduce you to first are stretch stiffness and bend stiffness. Stretch stiffness is the stiffness at which we attempt to keep this initial distance between points consistent, right? How far is this point allowed to move away from this point and essentially stretch this constraint? And this stretch stiffness is true for every independent constraint that is created between every single point. So all of these constraints are independently fighting to maintain their distance between the points that are attached to it based on this stretch strength. And this stretch strength is going up against all the other forces at play in our simulation, the gravity, the weight of the fabric itself, right? The other forces like wind and whatever else is affecting the thing in our simulation. So stretch strength is fighting that, but then you have the bend strength, or the bend stiffness, as it were. And this is a fight to maintain the angle between constraints. I'll move over here just for a second, because I can illustrate this better here by creating 3 points and connecting them with constraints. The bend stiffness is how far these constraints are effectively allowed to bend in on each other, right? If these start out straight, like this line right here, how far in are these allowed to bend in on themselves, right? Fold like a piece of cloth or something like that. And when you put these two things together, the stretch stiffness and the bend stiffness, you get access to a whole range of potential for a simulation that we'll see just upcoming here. And while this is a very simple explanation to kind of get us started, it will actually carry us through quite a bit of the Vellum simulation process, which is pretty cool. And also why I say it's a pretty simple idea overall. The power in this simulation style is handling it on the SOP level, right? Handling it before the simulation itself in setting up these constraints and all of their attributes. But don't worry if that sounds scary, because there are tools inside of Houdini that make it very easy to do. And I figure what better way to kick off this entire section than diving into a simple example to start. Let's begin by creating a geometry node, and go ahead and save this maybe as Vellum examples or something that you can just, keep on the side if you want it. But we'll call it build Vellum examples. Mark it blue. And inside, what do we want to do? Well, we can start by creating a grid, right? This is always the simplest approach to, making a baby's first cloth, so to speak. So we have a grid. It's just far too large. So let's bring it down to 2 meters by 2 meters. We'll leave the resolution of the geometry as it is. And I mean, what we talked about is we need points and we need constraints, right? Now we have points in this mesh that we are, working with here. So we can use these points. The thing is, we need to actually create the constraints and give them all of the attributes that they need in order to work properly. Now, normally, this would be quite the endeavor of, dropping a point wrangle and trying to code stuff and being a clever clogs. But lucky for us, the Houdini devs are the clever clogs and have given us a Vellum constraints node that we can simply drop down. By plugging in our required Vellum geometry, aka just our geometry input, the Vellum constraints will generate constraints for us. But the Vellum constraints node is incredibly flexible. And it all starts at the top with the constraint type. I'm not going to go too deep into this immediately. We will go through it in greater detail as we do the different projects and different approaches to Vellum simulation. But very quickly at the top, the constraint type dropdown is our window to the vast world of possibility for Vellum. If we click this dropdown, we can see there are a ton of different constraints that we can make based on our input geometry. And this changes all the parameters that we have access to because they all work a little bit different. By default, we have distance along edges. This, going back to my wonderful piece of art, oh no, I shut it. Oh no, it's gone. Oh, I don't think I'll ever be able to recreate that. But the default type is distance along edges. And this is pertaining to the first type of constraint that I was talking about, the stretch distance that is allowed. When we create our constraints with the Vellum constraints node, it creates, and I'll visualize this for us, this collection of constraints. Distance along edges, right? Prim lines that have been made along the edges and diagonally through all of the quad faces of our input geometry. But it's not just made these polylines, it has also created, in the geometry spreadsheet, attributes for these polylines in order to control the way in which they behave. Few of these being the actual tag, the name of the constraints, right? If I call this instead distance, now we can see this is the name of the constraints that we can call on later. Nice to keep track of this. But we also have a damping ratio. We have a rest length original, stiffness, and a type of constraint. The type is what I want to focus on first, the type being distance. This is the distance between the points that the constraint is trying to maintain as best as it can. How good it is at doing its job is directly reliant on how strong it actually is, right? The stretch stiffness is what dictates that. The higher the stiffness, the better this constraint is at maintaining its original distance between the points. The distance that is right here, the rest length original. When these polylines were created, it took a nice little snapshot of how far away the points were from one another and says, okay, this is our rest length original. We want to maintain this distance, and we will use the stretch stiffness in order to achieve that. If the forces in the simulation exceed our stiffness strength, then sorry, we'll do the best we can to return to our original length when we can, but there's only so much we can do, right? And this is what will create like drooping cloth that kind of sags and bounces. It's those constraints trying to pull back and eventually just settling at a further distance because of all the gravity force or whatever else is pulling it apart. And just so this is visualized, right, I will create a very simple Vellum solver. You can do this with me or not, but we'll come back to all of this in much greater detail. I just want to plug this in right now. And I'll make a little sphere. And I'll drop the radius of the sphere to, well, actually, I think that's fine. We'll just maybe lower the sphere overall. Yeah, we'll do something like that. Okay. Because now I can plug this in as a collision. And with these constraints created, and all of these, parameters being set however you want, it really is just that easy to hit play. And you get a simulation, right? Of cloth, kind of. Well, not really. Because if we look at it, what's the issue? Well, the distance is being maintained, we can see. These points are exactly as close as they were at the beginning, even when they are impacted in this way. If we were to lower the stiffness, and we'll go into this in greater detail as well, but if I were to lower the stiffness to something much, much lower, all of a sudden now, that distance is not maintained at all. So we would need something stronger. Apparently a lot stronger. And when we have something stronger, we can see that distance is attempting to return to its original distance, right? It's fighting to pull it back up, but the gravity's just too strong, and it results in a deformed final product, a stretchier looking cloth. I'll reset this back to the default. But there is a big issue with this cloth, if that's what we're trying to create, and it's the bend. Now, it does appear to be bending, and that's because it absolutely is bending. All of these constraints are free to bend as much as they want, because the bend constraint, the other type of constraint we were looking at, is not looking to allow it to bend a certain amount. No, quite the opposite. It's trying to limit how far it's allowed to bend. And without any bend constraints in, we get this. Infinite bending between these constraints, meaning sometimes they will intersect with one another. There's no limitation on the bending that is going on in this cloth. And so what we need is a different kind of constraint. I will sever these ties just real quick and delete this null. We have our distance constraints created, but let's drop down another Vellum constraints node and plug in all three streams between the Vellum constraints, which, just to quickly cover, is the geometry, the constraint geometry, and the collision geometry kind of through port. Very similar to what we were looking at in the flip section, right, with the SOT tools there. But everything feeds through to the next constraints, and then we want to create bend constraints as well. If we go to the constraint type, we can change distance along edges to, oh look, bend across triangles. Now, take a look at the parameters here. We've got stretch stiffness and all the controls that go along with it. If we change to bend across triangles, boom, it changes to bend stiffness instead. And we'll notice it's actually created bypassing this distance constraint creation just so we're only looking at the bend constraints, but it has created diagonal constraints 2 times over, creating 4 triangles for each quad in our simulation, allowing bending between all of these constraints to be enforced in some way. How much it's enforced is directly up to the stiffness values here. Now, with the distance constraints off, let's just plug this into the simulation and see the effect that it has. We're limiting the bend, so that's good, but maybe you see where this is going. If we hit play, it's great that the bend is limited, but the distance is not, right? So we need to also enforce distance. Both of these constraints sitting on top of each other, but both working independently of one another. And in the geometry spreadsheet, we can see we have our distance constraints, type distance, and we have our bend types, the Vellum constraints bend that we have tagged based on their operator string name there. So when these two things work together, now what we get is how cloth essentially works in the real world. And we have not only distance limited, but also the bend, and we're not getting that intersection anymore. You see it fighting to stay a little bit stiff, right? And if we drop the bend stiffness to something just incredibly low there, then we see it's, again, kind of bending in on itself. Or we can do the opposite and raise it all the way up and see now thing is stiff as a board. Fantastic. So that's cool. That's really nice to know. You know, we have our distance and our bend, and we control them separately in order to drive cloth. But the devs at Houdini know this, right? They are aware of the different applications that we want for our constraints, and so what they have done is made it very easy for us to toggle between the ones that we want. I'll delete this bend constraint and head back to the Vellum constraints one more time, because underneath the bend across triangles is cloth. And take a look at the parameters when I click on cloth. Now we have more, because we have control over the stretch stiffness and the bend stiffness inside a collection of one set of constraints that have been created, right? And all of these constraints now have stiffness values, but you'll notice there are distance and bend constraints created through just one Vellum constraints node, right? So it's consolidating, it's making it easier for us to work because, again, the flexibility of this unified solver in all that it can offer us can get a bit overwhelming. So it's nice to have this curated list of possibilities that it will start to explore through these projects.